We're looking at magnet notes, having done the magnet labs. And we have split this section where we essentially are looking at permanent magnets. And the second half we'll look at electromagnets. So in these notes we're focusing on permanent magnets. Well, permanent magnets have been known for millennia. The name may come from the fact that it might have been discovered in Magnesia, a place in Greece. And of course known in ancient times in China. Lodestone was the old name given for the magnetic mineral called magnetite, so we now call it magnetite, but it used to be called lodestone. And we have iron, cobalt, nickel, gadolinium. Those are 4 examples of strongly magnetic elements. We'll let you see if you can find out the 5th one. And now nickel magnet, well, Al for aluminum, then you have nickel, then cobalt. So this is a powerful magnet made of an alloy of those elements and a few others. And nickel and cobalt, of course, we can see are strongly magnetic, and the aluminum actually helps them maintain their magnetism as the alloy hardens. Now, I should have said north-seeking pole geographically, so I've added it over here. So north-seeking pole, it means it seeks the north end of our Earth, is called an N-pole or north pole of a magnet. And the south-seeking pole geographically is the south pole or S-pole of a magnet. So we look at the laws of magnetism. We know that opposite poles attract, so north and north, and like poles repel, and that's likely something you discovered in the lab. Magnetic lines of force. We use these lines of force to represent a magnetic field. The magnetic field is the area around a magnet where its effects can be detected. So by definition, a line of force shows the path a north monopole would travel if it were free to move around a magnet. So this is if we could get down to a one-poled magnet. If we split magnets, keep splitting until we get one pole. In practice, no monopoles exist. So mono means one, so that's why it's a one-poled magnet, and this is what it's trying to show, just a one-poled magnet. Since the lines of force show the path a north monopole will travel, they always go from north to south. And lines of force do not cross each other. One of the things you're going to be asked to do is to draw lines of force representing magnetic fields. And you want to put enough lines in, and you have to label their direction, but you don't want to put so many in that they're going to cross over. The closer together lines of force are, the stronger the magnetic field. And we will find that the ends of a magnet where we have the poles are the strongest because that's where we have the more lines. So here's an example representing, now it's not the best example here because it makes it look like some of these lines are crossing or touching, and they're not supposed to do that. But the bottom line is here's our north, and so the lines curve and curve and curve towards the south. So they come in the south and they leave the north. All right, that should be it for that page. Now the Earth, it was discovered, is a giant magnet, and this is why compasses are helpful. Unfortunately, the magnetic North Pole is not at the exact same location as the geographic North Pole. So geographic is the North Pole, which represents the axis of the Earth on which it rotates. But the magnetic North Pole is going to be where it's strongest in our northern hemisphere. And there's a southern magnetic South Pole as well. Now this 1,500 kilometers is going to change because the magnetic field is actually wandering. So it was in Canada and still remains in Canada, but it's heading into the ocean. Who knows where it's going to go. And it turns out, historically, the Earth's magnetic field has reversed many times, and from Earth Science in grade 8, you should know that already. So scientists are studying those reversals. They want to know how fast they are, and they're really interested in what happens during the reversals. How long is the magnetic field shut down for? Because the magnetic field actually helps protect life on Earth. The end pole of a magnet points the magnetic North Pole. And you say, gee, but we just said opposite poles attract. Well, what we're saying is it points to the north end of the Earth, but the north end of the Earth, that north magnetic pole, must actually be the south pole of a magnet. So that's how we get around that. The Earth's core, we know there's an inner and outer core. And so the outer core is going to have a liquid layer, and that's believed to be what generates the Earth's magnetic field. Northern lights are also known as aurora borealis, and the southern lights, aurora australis. Think of Australia. So this is, if we could take a compass in space, this is what it would do. And we're really interested in what lines of force do on the surface. Say we're out in the woods, don't have GPS, and we're navigating by compass. And so here would be the north magnetic pole, and up there is the north geographic pole. Now we want to explain magnetism, and the domain theory of magnetism is what we used. So domain, so let's think of a bar magnet. A domain is a region within that bar magnet where we have a group of magnetized atoms that have their magnetic fields aligned. In other words, it works together. So each domain is itself a tiny magnet, and if we can get those domains pointed in the same way, then we have magnetized it. So you can have a magnetic material, but only if its domains are aligned do we consider it to be magnetized. If we demagnetize it, it means we have scrambled the domains. They're randomly arranged. And so those are words you have to get used to. So over here, it's all over the map, unmagnetized, and here, most of the domains point to the right. That's considered to be magnetized. So we want to know how we can magnetize it and how we can demagnetize it. So magnetizing, yes, we have to align the domains. One way, and you did that with the test tube magnet, is by slowly stroking a magnetic material repeatedly in the same direction with one pole of a magnet. So here's the old, so we're saying, hey, we took the north end and we kept going like that, took it away, did it again and again and again. And each time we align more and more domains and it becomes more magnetized. Induction or conduction method is you touch a magnetic material with a magnet, and that's what you did with the iron spike in the last lab, and it creates the opposite pole. So here's the south, it's going to create the north pole in the material we're trying to magnetize. We can also use a magnetizer to do that, and we'll talk about that more when we do electromagnetism. Demagnetizing, we just got to scramble the domains. So if you drop a magnet, if you bang it against a desk, if you heat it up, all those things scramble the domains and will cause it to demagnetize. Improper storage, that would be if you put two magnets together, north and north. In fact, you should store them north and south and have a keeper to make sure they stay magnetized. And that's what it says here. This is proper storage. So there we are. And the keeper, just going to be a magnetic material, helps reinforce the field. Now, some of these uses are becoming quite obsolete. So we have door catches, like in a kitchen. Certain can openers, like the wall-mounted can openers, often will have that to hold the lid after you cut it off. Speakers, phones, the fridge door, you can stick magnetic things on that. You don't have to just use grape juice that you spilled on the door to stick things on. Lots of toys involve magnets. Compass does. Credit cards may have a magnetic stripe. And motors, electrical bells, now it says electric motors, kind of redundant. In the old days, and I actually still have videotapes lying around and probably audio tapes, and a computer disc used to be magnetic. And so you could really wreck those things if you ran around with a magnet. Older TVs actually had magnets with them, and I used to take a horseshoe magnet to one of our TVs just to put a nice rainbow spot in one of the corners of the TV screen. So other things that maybe you'll find out about as we go along are these terms. Not too big an issue. You will be asked about magnetic declination. So hopefully that's all good. But those are your magnetism notes, and those should help you with the magnet questions. And you also have a photocopied chapter. The first sections, the 1 and the 2 sections of that chapter, are about permanent magnets.